Welcome everyone, my name is Mariusz Budziński and I'm data scientist at CodiLime.
And I am Tomasz Janaszka and I am solution architect at CodiLime. Today we would like you to present how to use AI ML techniques for proactive detection of network overload. Before we start, we would like to encourage you to check out our other webinars available on our YouTube channel, especially those in the area of data science and data engineering, such as AI ML for networks and effective data processing techniques. The topic we would like to present today is not an easy one, but at least our agenda is quite simple. We will introduce you into the problem, putting it into a specific networking context. Next, we demonstrate the architecture of our proof of concept, explaining its crucial components. We will also show some results for the example network. And we would like to, at the end, we would like to conclude summarizing the functionality of the PoC. Also, we would like to say a few words about the potential extensions and of course, to indicate some business benefits that can be obtained if we decide to deploy such a system. At the end, we will have some time for answering your questions. So, introduction to network overload issues. Let us explain such issue in the context of IP core network that consists of the car routers marked dark green in this slide and denoted by the labels R1 to R11. Such a network is transiting the traffic between any pair of edge routers marked with limb color and denoted here by the capital letters. The edge routers can be access routers, BNG routers, also evolved packet cores, also the access to the tier 1 internet providers. This topology presented here, this is the example topology, and the labels on the links represent the current network capacity expressed in gigabit per second. So such a network are designed to be resilient against assumed failure scenarios. We will explain this later on, and with some over provisioning level. So which means that the network is oversized in order to carry the traffic which is higher than usual, for instance, as one of part of the network is, for instance, under failure. And we should also know that the traffic is changing over time. So usually it has the increasing trends. So the network design at some point with specific capacity will become insufficient in the future if the traffic is growing. So that's there is a need for continuously monitoring the traffic and continuously monitoring if our network is keeping the assumption about the resilience level that should satisfy.
Given the context introduced by Thomas, we want to address the problem of detecting future overloads in the network. That means, first of all, we want to know when the overloads will be present in the network and which particular elements of the network will suffer from the lack of capacity. We enrich our analysis with different failure scenarios to make sure that our network is resistant to them. As a solution, we propose analytical system that consists of 4 main points. First, we collect traffic flow bitrate data. Then we forecast such traffic flows for a given forecasting horizon. And then we emulate network for this forecasted traffic with different failure scenarios. And at the end, we report expected overloads.
And this is the high-level architecture of our proof of concept. First of all, we need to organize appropriate data we would like to work on. So from our network, we should organize the retrieval of the traffic measurements and also retrieval of the network topology, capacities, and routing settings. So we assume that it is possible. We will talk from which sources could be used to retrieve such data on the next slides. But now we would like to focus on the two major components of our PoC. This is the machine learning-based traffic forecasting engine that is working on traffic measurements and predicts the future traffic conditions. That is the major input to the network emulation engine that is examine how network will behave for those traffic conditions in the future, assuming resiliency requirements that we would like to meet. So the output of this network emulation engine at the flow level is what are the future expected congestion on which network elements and when. And also our tool is producing what have to be done in order to avoid them. So now is the time we would like to say in detail how we build machine learning based traffic forecasting engine, but before we start talking about how the data are processed, we would like to explain what the traffic data we need in our tool. So we would like to have so-called end-to-end traffic flows. So we would like to have the measurements about the bit rate in time between any pairs of edge routers. Usually such a data are being collected if we have analytical tools and collectors of net flow records that are collecting the data from all the devices, and usually such a tool, such a system allows to define some filtration queries. So this is one example of end-to-end traffic flow from the edge router F to edge router B. In order to get such a statistic about the bit rate, usually in such a tools can we define the filter that we are interested in the traffic that is incoming to router F through these down interfaces 1 and 2, and destined it to the addresses, network addresses that are exposed by the edge router B. How we model end-to-end traffic flows strongly depends on how we are routing the traffic flows in our network. Here we assumed that we know all the end-to-end traffic flows between any pair of edge routers. But in reality, for instance, if we forward the traffic IP, for instance, IPv6 in different way than IPv4, then in such a tool, we will have to define two end-to-end traffic flows between those two edge routers. And this modeling have to be done. It is an important part of building such tools, and should be done in strong cooperation with the network engineer that is knowing what are the routing rules in our network.
Here we have on this plot exemplary traffic flow bitrate from our database, a few months perspective. What you can clearly see here is a strong increasing trend, which represents long-term behavior of such traffic flow. And this is very important in terms of detecting future overloads. We can also look at this traffic flow in a shorter perspective. Here is an exemplary week. We can clearly see the daily pattern, which changes from day to day, especially weekends, characterized with much higher amplitude than the working days. Going more locally, this is an exemplary day of the same traffic flow. We can see dots which represent single measurements because we gathered data hourly, and the traffic flow is increasing here up to its peak hour, which is 11 p.m., and then it's constantly decreasing. As I said, one of the most important feature in terms of future overloads is trend, which is long-term behavior of a traffic flow. We have different kinds of trends in our database. Here are 3 exemplary. The first one is linear increasing trend, the second one is linear decreasing trend, and the third one is logarithmic trend. Another feature important in terms of overloads is called seasonality. Here we have exemplary 2 weeks of an exemplary traffic flow. We can see that those 2 weeks are very similar to each other with small fluctuations. We call such a pattern the seasonal pattern. Here we have 1 week periodicity. In our database, also we have different kinds of daily patterns. For instance, the Lime one has its peak hour around 8 p.m. and the green one, on the other hand, has its peak hour around the noon. So they compensate each other. They can go through the same link at the same time, and they will not result in overloads. And we have the blue one as another example. In our database, we have over 70 different such patterns. As Thomas said, we are focusing here in traffic flow forecasting. So we take historical data for each traffic flow separately. We optimize machine learning model to such kind of data. We fit its parameters. And after the model is fitted, we can make forecasts into the future for a given forecasting horizon. And the blue line represents the forecast for this traffic flow. As I said, we make forecasts for each traffic flow separately from our database. To give you more details about our machine learning processing pipeline, here's a graph that represents it. So we start with traffic flow, its history. Then we have block called pre-processing. Here we input gaps and correct outliers. As a forecasting approach, we decided to use the composition approach. We took seasonal and trend decomposition with Loess. It's additive version from stats models library. After the decomposition, we have trend and seasonal component. So we forecast separately those 2 components. For trend, we feed linear or logistic curve from scikit library. And as a seasonal model, we use seasonal naive model from sctime library. Then we join those 2 forecasts, we add them together to obtain the final forecast. In each block from our pipeline, we can use alternative methods. If you want to include more complicated shapes than the linear or logistic curves, you can use methods like Gaussian process, neural networks, assemble models. For seasonality, you can use models like seasonal ARIMA models, TBATS models, which can handle non-integer valued periods, regression models, and much more. As a decomposition, you can try to use multiplicative version of decomposition. You can try different approaches for decomposition, like empirical mode decomposition, singular spectrum analysis, or even you can try approaches without any decomposition at all. As I said, we forecast each traffic flow for a given forecasting horizon, and such forecasts are inputs for the network emulator engine.
Yeah, so the basic data we have, the forecasted traffic conditions for the future. So next time is just to use network emulator engine. So this is the software, a piece of software that its main objective is just to compute the load on particular network elements and to indicate those one with insufficient capacity to carry expected future traffic. So as input, network topology, capacity and routing settings, forecasted traffic conditions, and also potential failure scenario that we would like to examine the network, how it behaves under on different states. As the output, we would like to have load on the links in time and for each potential failure scenario. So we developed such an engine using Python language, and this is also the bunch of the crucial libraries we used: NetworkX for analyzing the network topology, NumPy and Pandas standard libraries for processing time series data. We store the results into the database InfluxDB, which is the database specialized for time series data, and we use Grafana framework for building useful dashboards.
Okay. We have already used the notion network resiliency. Now it's good time to explain the term more detailedly. So we define 4 states that network can be in. The first is called nominal state, when each component of the network is working properly, so there are no failures at all. And then we define 3 failure states. The first one is called single node failure, when the single node stopped working. So each link that goes through this router is not available, and of course the routing needs to be changed, and that's why we can have overloads. The second failure scenario is called single link failure, when the single link between 2 routers stopped working. So similarly, the routing needs to be changed, and this can cause overloads. And the last failure scenario, called partial link failure, if you take a link between 2 routers and the link consists of a few fibers, and let's say one of them or a few of them stopped working, then the link is still available, but it has much lower capacity than the initial one, and the routing is not changed here, and this can cause overloads. And now we say that the network is resilient to, let's say, single node failure if for any node failure the network is capable of carrying all the traffic. There are no overloads in such a network. And similarly for different failure scenarios.
Also add that usually the probability of the partial link failure is much more higher than the single link failure, and single link failure is much more probable than single node failure. So it's worth to note here. And now we would like to say a few words about how we are processing the routing data and what are the routing data that we are processing in our PoC. So this is the same topology, but this time on the links we denote the routing metrics from say IGP protocol, based on which usually the routing paths, shortest paths according to shortest paths rule, are computed in the network. But in reality, usually in such a network, we are using a couple of routing protocols, IGP, BGP, or MPLS switching. So the objective is to take all these settings and to determine what are the routing paths in our network for each, say, between any pair of edge routers. How to obtain such a data? There are some specialized tools that we call commonly routing agent. So this is the kind of analytical tools that are active listeners of the, say, routing messages in the network, and such a tool are able to expose the fresh information about the network topology, capacity, and routing settings in the concise form for the further processing. And this is the easiest way to obtain such a data. If we are not, if such a tool are not deployed, there is no network toolset that assists our network. Then if we think about deploying such a systems, we might be forced to analyze the data or retrieve the data directly from the routers, analyzing the routing information base or forwarding information base, also analyzing the routes exposed by the route reflectors. So it's not easy task. In general, here in the POC, for the demonstrative purposes, we assume that the simplest scenario when we have the IGP metrics done here for each edge, based on which we are computing the shortest paths, and usually such metrics are distributed across the network using link state protocols like IS or OSPF. Our tool is computing the routing paths for each between any pair of edge routers. This is the example of routing paths from edge router A to edge router H. So here we see that there is a situation when starting from router R2, we have two shortest paths, here and here. So we call such a situation like equal cost multipath. And the labels denoted here on these arrows represent what part of the whole traffic between A and H are carried by particular links in our network. So this is the routing paths for the nominal state, but it is being changed if we have some failures in our network. For instance, if we have a single node failure of the core router R5, we have only one single path here. And comparing to the previous situation, these links will carry the whole traffic between A and H. So in some situation when there will be no enough capacity, they may cause the overload here and here. Similarly, for another failure, we could see how the routing is being changed for the link failure. And for the partial link failure, the routing is the same as in the nominal state, but during the failure, we can use only part of the capacity here. This is in nominal state is 400. If we have the partial link failure, one interface is, for instance, failed, we can use 300. So such a situation may cause also the congestion. So we are collecting all these routing paths for each end-to-end between any edge routers and for each failure scenario. And having such a data, we can easily detect the future congestion. Just to recap, so we have the traffic forecast for the next month. In our POC, we have the resolution of data of 1 hour, and we have computed routing paths for all network states, including nominal and any potential failure scenario of different types. So we have 75 in total such network state we would like to analyze. And computing the load on the link is just straightforward, some summation and multiplication of the routing paths and this coefficient that I presented before, and times the predicted traffic for each end-to-end traffic flow allows us to compute what is the traffic expected on each link for each hour in the forecasting horizon and for each potential failure scenario. And just comparing the expected traffic to the current capacity, we can indicate the time and which network elements are expected to be congested. So now we would like to present results of our POC, some dashboards, Grafana dashboards that we made. So this is the first dashboard that is focusing on how many days we have to first congestion. These are results for the nominal state, and always this dashboard is presenting what is the time from our analysis date. So we did the analysis the 1st of August. Based on the results, we are showing in time the bars. One single bar is its interpretation is that if we see at least one link that is expected to be overloaded in the future, then we have the true. So this is the bar. And so we have the time. And also we have how many links will be overloaded, how many end-to-end traffic flows are affected by by such congestion, and in particular which link and which network state is causing. So here we assume that we are increasing trend of the traffic, so such a situation will be met into the future more often and more often for the nominal state if we do not upgrade our network or reconfigure whatever. So this is the first dashboard, and we can easily show also such a situation in the in another representation on the graph, on the network graph. Here on the labels we have the rate of the traffic divided by the capacity. So we detected that the first congestion will be in March next year, 70, at 8 p.m. for the nominal state, and such a situation means that the edge from the router 8 to D will be congested because the traffic will be the same as the capacity. So this is the situation that we mark as potential overload, and we mark such links with red color. So this is another representation of what we discovered here.
Here we have single node failures, and we have 124 days to the first overload. This will happen 3rd of December this year, 8 p.m. And there will be one link which is overloaded from router R1 to R2 because of the failure of the router R4. We can visualize the situation in the graph. So the router R4 stopped working, so the link between routers R1 to R2 attained its maximal capacity 100%, and it's overloaded. For the single link failures, we have 229 days to the first overload. There will be two possible links that can be overloaded because of the different possible link failures. We visualize one of the failure when the link between D and R8 stopped working, so the link between R7 and D attained its maximal capacity 100%, and we have overloads.
And the results for the partial link failures, and here we can be a little bit surprised because the time to the first congestion is only 40 days. So it will happen when we will have the partial link failure of the link R3 and G. We can visualize this. So this is the situation. Normally this link has the 200 gigabit per second, the speed. But if one of the interface is, failed, then we can only use the half of this capacity. That is not enough to carry the whole traffic that our system is detecting and marking the situation and the link red. So it might be a little bit counterintuitive, because if we see the load in our network for the same date as for this partial link failure, and if there is a whole link is not available, so we have the single link failure, our system is not showing any congestion in our network. So the capacity is enough to cover the whole traffic. This is because here the routing is changed dynamically, but in this situation of partial link failure is not. So this is a kind of counterintuitive, but our system is able also to detect such situations.
And here is network. This dashboard represents network resiliency evaluation. So we have here the summary when we have overloads because of different failure scenarios, and the first overload will happen because of partial link failure in 40 days, possible partial link failure. This plot represents the link between router R1 to R2, and we perform such analysis to every link from our network. And the green traffic represents the worst case scenario, the maximal load on this link, taking into account different failure scenarios. And the blue line represents current capacity. And the lime one represents the required capacity to don't have any overloads on this link. So we can see here two steps. That means we should here upgrade the link by 100 gigabytes per second. The first upgrade is December this year, and the second upgrade is June next year. This table gathered all recommendations, upgrades that we recommend you to perform to prevent any overloads in a given forecasting horizon. And so we have here the link, and the required capacity upgrade, and the required capacity after the upgrade, and which failure scenario enforce on us this upgrade. We can, for curiosity, just apply three first upgrades which are in this year. So here we applying those three upgrades to the network. This is the situation before. So we have before the upgrades. So we have 40 days to the first overload because of partial link failure, and we have 124 days to the first overload because of single node failure. After the upgrade, for partial link failure, we have now 229 days to the overload, and because of single node failure, we have 229 days. So applying just three our recommendations, we postpone the overload in the network by a lot. And if you would apply all of our recommendations, you won't have any overloads at all.
Yes, Mariusz said, so the basic, the basic way to avoid expected congestion is to buy a new capacity to the network, but it's not the only solution. Here we would like also to use our tool just to check if we can improve the network configuration in order to have better performance without investing into the upgrades. So here we just prepared the same topology, but we modified the routing metrics in our network. Having some skills, we know that if we have in the network more equal cost multipaths, usually it is better, the load is better balanced in our network. So we just follow this, assumption to modify the routing metrics in that way, and we use our PoC to check the consequences of that change. So this is the known results for the current situation with before our change, and this is for the new scenario. So here we see that the performance for particular failure states were improved because we have the longer times to the first congestion without costly investment into the new capacity. Here we would like to stress that it is not a situation that we can always improve the routing. At some point, there will be no optimal solution. We will have to buy a new capacity. But if we have some not optimal settings, then we can also use such a tool to try to find better solution. And now we would like to conclude.
Okay, so our PoC covers, first of all, a machine learning-based forecasting engine, a network emulator for different failure scenarios, proactive congestion detection, as well as network resiliency evaluation. It gives you recommendations to avoid, to prevent overloads in your network, and verification of those recommendations in terms of network performance.
Yeah, so above this implemented, we would like to say a few words about the possible extensions, because what we showed you, the results are for the single analysis given at the given point in time, date. So it is quite easy to imagine that such a process could be run as a cyclic process, producing the fresh results, for instance, week by week, taking into account the fresh data about the traffic and the fresh information about the network configuration. So in that way, we could have some kind of continuous system that is telling what is expected to be in the future with our network. Also, we demonstrated that the system is giving you the advice which network elements have to be upgraded and when. But additional, say, checks can be integrated in such a system just to check if it is feasible. It means that we have to look into the current configuration particular routers and to see if there is a free capacity and such an upgrade is possible, and eventually what is the cost evaluation of such upgrades. Also, we mentioned that different failure scenarios have different probabilities. If we can retrieve such information from our experience of our network, we could also weight the results of such a system, also taking into account the probabilities of particular failure scenarios. In that way, we could show that there is a danger of the congestion, but also to provide what is its probability. And I can easily imagine the situation when okay, we know that there is a danger, but the probability is very low. And if we at that time are short in money for the investment, we can postpone such upgrades in a consciously way. So also we demonstrated how the network configuration can be changed. We made such exercise using our skills and do it manually, providing new routing metrics, changing the configuration, and we used our tool for the evaluation if it helps, if it improves our performance. There is a place when we can apply additional optimization algorithms, also including reinforcement learning, because we can just apply some steps and check the results. So in that way, we could just try to find better solution and give such recommendation to network engineers. And finally, if we assume that such analysis we are repeating in time, week by week, we can easily also develop anomaly detection regarding the traffic conditions, just comparing what is measured in particular weeks and what we predicted last week. So if the difference are too high, it is also important information for our engineers that they have to check, and with the high resolution of end-to-end traffic flows. Also, we would like to say a few words about the business benefits. So our results, the PoC results, have the proactive, proactively provide what will happen in the network, and also are telling us what to do in order to avoid them. So problem avoidance is usually cheaper than problem solving. That's why we could just expect some savings, for instance, omitting the costs related to the flood of customer complaints. Also, if we know what we do and we could verify if our changes in the network will help, we could better optimize the schedule for the necessary works, maintenance works in our network. We clearly showed that if the configuration network is not optimal, such a tool can be used to improve routing and topology, just to postpone some necessary investment into the network capacity. In that way, we can build the network that has lower of a provisioning level. So it means it is less oversized, better adjusted to the expected traffic for the future, also with keeping in mind the resilience requirements and various probabilities of failure scenarios. As a final word from my side is just we demonstrated the problem of the future congestion for the IP core network. So, but the general idea, general approach, just to forecast the traffic using machine learning techniques, for instance, as we did here, and evaluate the network at the flow level, taking into account various network states, can be applied to different networks. And I hope that this talk will be also some kind of inspiration when similar approach can be applied in your environment, in your network.
And now it's time for a Q&A session, so feel free to ask questions. Okay, we have the first question. How big of a network did you simulate? Not linked numbers.
So the idea of the POC was to show the idea how to merge the two technologies, machine learning and the network emulation. So this is the computation we did for this example network. I think this is the question about the solution scalability. For sure, in the reality, there will be the thousands of the end-to-end traffic flows and much more. It depends on the particular setting. So it can be quite computationally intensive, such a system. So maybe very short answer for this question. But preparing the data for this talk, we didn't analyze a bigger network than presented here.
Mm-hmm. Which tool did you use to simulate?
Yeah, we used our network emulated at flow level was written from scratch by us. So we developed this tool by ourselves completely, and we only use the network X library just to take some functionality for computing the shortest paths in the network graph.
When you consider the link congestion, what is the threshold?
Yeah, this is the question about what is the threshold when we consider that the link is overloaded. So for demonstrating purposes, we use the 1, which means then when the traffic is crossing the capacity, then we treat such a situation as a congestion. We know from the operational point of view that this threshold should be usually 0.8 or 0.9, but in the tool it should be a parameter, in fact.
Mm-hmm. Next question, can you simulate a traffic pattern change when a new link were to be added between two backbone nodes?
Yes, exactly. It's just as we presented here. So this capacity upgrade is not. This is, let's say, another say type of topology that we input to the analysis. But also we could just create a new edge and apply, of course, some routing metrics to that edge and to change what is being changed around. Also, perhaps adding the failure scenario, because if we have a new link, then we have to define the failure scenario for it. Yeah, and that's all. It could be used so that I mentioned that not only the routing could be optimized, but also the topology, which means that we are adding or moving some links between particular routers.
Is there any part of the code you can share?
Not yet now, because it was we worked 2 months together on this. So our first objective was to create the POC with all the consequences. This is a POC, but we will try to think if
it's worth considering.
Yeah, it's worth considering if we could prepare it to be shared with the broader audience also. But we are not ready for it now. Yeah, in that sense.
Okay, I think there are no more questions. So one more announcement. We ask you we'll send you a quick survey about our webinar, and you can just give us a note how you feel about our webinar to make it better in the future. So thank you all for participating here. And see you. Bye-bye.
Thank you for joining us.